Since we are gaining so many tools for our statistical toolbox, many of which can be used to analyze the same set of data, it's going to be important to know how to choose a particular method for analyzing the data. That's where relative efficiency can come in handy. Relative efficiency is about choosing the most powerful inferential methods for a given circumstance, scenario, set of data. There are two types of relative efficiency that we will consider. The first is local relative efficiency. Suppose that either of two hypothesis testing methods can be chosen. For example, you might be able to choose the sign test or the match-pair-Wilcoxon. Or you may consider the match-pair-Wilcoxon or the match-pair t-test. First, determine the nominal significance level. That is, what is the maximum type 1 error that you're willing to live with? Set an effect size, and then set the desired power. If you've learned about power, you'll know that if we know the type 1 error rate, the effect size, and the power, we can calculate n, the sample size. So here we're setting 3 of the 4 variables, everything except for n, and we should be able to calculate n. Let n A and n B be the sample size needed for method A and method B to achieve the stated power. So here n sub A represents the sample size we need for method A in order to achieve the desired power at the nominal significance level we chose and with the effect size that we chose. N sub B is similarly the sample size needed, again, to achieve the desired power with the stated effect size and with the nominal significance level. Note that the significance level, the effect size, and the power are the same regardless of which method we're looking at here. So we're obtaining 2 sample sizes, one for each method, with all the other variables held constant. The local relative efficiency of method A compared to method B is given by the sample size needed for method B divided by the sample size needed for method A. And we symbolize this local relative efficiency with epsilon sub A comma B. So think about this for a moment. Suppose that more individuals are needed for method A than method B. Then the n in the denominator is going to be larger than the n in the numerator, and you'll get something less than 1. That would indicate that the relative efficiency of method A compared to method B is in favor of method B because that efficiency ratio is less than 1. So if I was to say that the local relative efficiency for the match-pair-Wilcoxon compared to the match-pair t-test is 0.9, that tells me that more subjects are going to be needed for the Wilcoxon than for the t. In fact, the ratio is going to be 9 to 10. Whereas I would only need 90 for the t, I would need 100 for the match-pair-Wilcoxon in order to obtain the same power. Now that's just one example. The example could be flipped around the other way depending upon the circumstances. It might be that if I want to know the local relative efficiency of the Wilcoxon compared to the t-test, that the Wilcoxon only takes 50 subjects for the same power that takes 100 subjects for the t-test. In that case, our ratio would be 100 divided by 50, or 2. That would tell me that the Wilcoxon was twice as efficient as the t-test, meaning we need half as many subjects. Think on it a little bit. I know it's confusing when it's first introduced, but if you try out a few ratios on your own, indicating which test is A and which test is B, you'll start to get the hang of it, that when looking at the efficiency of A to B, if more people are needed for A, the efficiency is less than 1. If fewer people are needed for A, that's a good thing, and the efficiency is greater than 1. If the same number of people are needed for A as for B, the local relative efficiency would be 1. Now, what makes this local is that we're here looking at a particular scenario, a particular distribution of data, a particular effect size, a particular significance level, and a particular power. Therefore, local relative efficiency would have to be calculated for every possible situation. If we have a set of data, we would have to estimate what the population distribution is. Then we'd have to set an effect size and a significance level and power and do a sample size calculation using sometimes complex formulas for both method A and method B. So although local relative efficiency can tell us for a specific situation which method is the best to use, it's very cumbersome. An alternative is to use asymptotic relative efficiency. Suppose that the effect size is reduced. That is, we start with some effect size, say the difference between those means is 1 standard deviation, but now we reduce it to 3/4 of a standard deviation, and 1/2 a standard deviation, and 1/4. If you're going to maintain the same power when you reduce the effect size, you're going to have to increase the sample size. So as effect size moves closer to 0, sample size is going to get larger and larger and larger and larger. Well, it turns out that the ratio of the two sample sizes that we defined for local relative efficiency, if both those n's are getting large, that ratio fortunately approaches a constant. And that constant here is denoted L. L is the asymptotic relative efficiency. So the asymptotic relative efficiency is the efficiency of our two tests as we move the sample size closer to 0, thus increasing, as we move the effect size closer to 0, thus increasing both sample sizes. And the ratio of those sample sizes is going to converge on a limit notated here as L, and that's the asymptotic relative efficiency. Whereas the local relative efficiency is specific to an experimental situation, the asymptotic relative efficiency is general for a given distribution. So if I know a distribution and I want to calculate the asymptotic relative efficiency for two procedures, say looking at the match pair Wilcoxon, comparing it to the match pair t-test when the distribution is a logistic distribution, once I calculate that asymptotic relative efficiency, that's now a set number that I can make note of and is always the case for every situation where we have a logistic distribution and we're comparing the match pair Wilcoxon to the match pair t-test. That is true for any two tests that you take on for comparison, given any distribution. So if the matched pair Wilcoxon has a certain efficiency compared to the t-test for the logistic distribution, it likely will have a different efficiency when we look at the Laplace distribution. However, once we've calculated the efficiency for that distribution, that's it. It's a set number, so we can publish those numbers, and in fact those numbers are published. We can look up asymptotic relative efficiencies so that we know for a particular distribution which test is most efficient. Now it turns out that local relative efficiency changes from situation to situation, and in fact that's what's going to be most important to us, because local relative efficiency tells us what the efficiency is like in that given situation. The nice thing though is that local relative efficiency and asymptotic relative efficiency are typically similar, especially when we have a large sample size and small effect size. So the times that they're likely to be somewhat different from each other is if we have small n and we're looking at larger effect sizes. In that case, we could set about trying to estimate local relative efficiency, but my experience and studies have shown that use of the asymptotic relative efficiency instead of the local relative efficiency works pretty well. That is, the deviation between these two is not that large that we have to be too concerned. And obviously there's a huge advantage to using asymptotic relative efficiency because we have a set single number. We don't have to actually sit down and do calculations. Note this also, that if you're calculating the local relative efficiency, that's only going to be an approximation anyway. And so the approximation, if it's a little bit off from asymptotic relative efficiency, well, in fact, it may be an approximation that, if we had gotten a better approximation, would have been right on asymptotic relative efficiency. That is, there's not really a good argument for using local relative efficiency. You have to estimate what you think the distribution is, and then you have to calculate under what you think the effect size might be, which of course you really don't know. Let's take a look at an example. Pre-post difference scores are used to assess the value of a treatment. Suppose the distribution of these scores is normal, with a standard deviation of 21.8. The match pair t-test and the sign test are both appropriate to test the hypothesis that the mean difference equals 0 versus the mean difference does not equal 0. Okay, as you know, the t-test is going to take advantage of the quantitative nature of the data, but as you also know by now, sometimes that's not an advantage. Sometimes just looking at whether the difference score is positive or negative is going to be more powerful. Now, without going any further, you should tell me which of these procedures is going to win in this instance, because notice the supposition. Suppose the distribution of these scores is normal. If you truly can suppose that the scores are normal, then in fact the t-test is going to win, because the t-test is an optimal test when the scores are truly normal. The reason that we have introduced nonparametric procedures as competitors is because we don't usually know that that's the case. Even when the distribution has a bell-shaped curve, it may not be normal. It may in fact be closer to a logistical model. But in this case, in this example, the t-test is going to win. Let's go on and see this carried out. So now we set the type 1 error rate at 0.05. We set power at 80%. How do I know that? I'll remind you that beta is type 2 error, which is 1 minus power, or power equals 1 minus beta. So power equals 1 minus 0.2, which is therefore 0.80. So we have type 1 error at 5%, power at 80%. And let's suppose that we know the effect size is such that the difference is actually 8. So we're looking at this specific alternative mean. We don't know this for a fact because we only have sample data and we're estimating a population effect size. But here we're positing an alternative hypothesis that the mean is 8. Well, if we do the calculations, which are not easy to do, we'll find out that 46 participants are needed for the t-test and 74 are needed for the sign test. So if I'm looking at the local relative efficiency of the sign test to the t-test in this particular circumstance, when we have set alpha, we've set power, we've set effect size, and we know what the distribution is, then we can take 46 divided by 74 to find out that the local relative efficiency of the sign test to the t-test is 0.62. Another way of saying that is that for 62 people needed for the t-test, we need 100 for the sign test. It turns out if you look up the asymptotic relative efficiency that's already been calculated for us for a normal distribution, that asymptotic relative efficiency of the sign test to the t-test is actually 0.64. Notice the small difference here between 0.62 and 0.64. And because I do not know if the effect size is really 8, and because I do not know if the distribution is truly exactly normal, that 0.62 is an approximation. So it seems to me that 0.64 is reasonable to take as an approximation to compare the sign test to the t-test. And in this class, rather than computing local relative efficiencies for each test that we do, what I'm going to do is focus on asymptotic relative efficiency, because we know that gives us good principles for determining the relationship of one test to a possible competitor test. I'd like you to know about both local relative efficiency and asymptotic relative efficiency, but when I make comparisons, I'm typically going to focus on asymptotic relative efficiency. So now we have a terrific tool for comparing two possible tests for doing a hypothesis test with the same set of data. We can look under the distributional form that we believe to be the closest model to the correct one. We can see what the asymptotic relative efficiency is, and that will lead us to make a choice of one procedure as compared to another procedure. So you'll see that done when we look at competitive tests. We'll take a look at their relative efficiency and help us make a decision that way.